A gente está gravando a sala, então, por enquanto o microfone...
Então vamos lá, viva a revolução. Let's see, so I'll continue from yesterday, and only the people who are really starving for knowledge are here today, right? So, okay, so let's see. I'll pick up where we left off yesterday, and I'll continue. Is everybody okay with English? Okay. If you have questions, please raise your hand. Feel free to ask. In fact, I usually say to my students too, my graduate students or my undergraduate students, if you want to show something on the board, come up, grab the chalk from my hand, and start writing. That's okay too. Really. So let's see. So where are we? We left off with the example of in 2 dimensions of Michel-Dion's theorem. Let me write the general theorem now, in the complete generality. So, teorema de Michel-Dion, 1988. So, fix any rational polytope T. So again, polytope, you know what it is, a convex hull with a finite set of points in Euclidean space. Rational means that all the vertices are rational points. So all the coordinates of all the vertices are rational numbers. And let the vertex tangent cones be, let's write the vertex tangent cones KV1 to KVN, and we saw what they are. So if you have a triangle, the vertex tangent cone at this vertex is this. It's unbounded. And then the integer point transform, and I'll remind you what this is in a second, is the sum of the integer point transforms of the tangent cones. Yeah, so this is the famous Brion identity for discrete. Everything is discrete, meaning these are sums, not integrals. Some people call this discrete Fourier transform. But so again, just to remind you, so this is the integer point transform, which is a discretized Fourier transform. And since P is compact, by definition it's compact, this is a finite sum. But also, when P is not compact, when it's a vertex tangent cone, it's the same thing, except you have to be careful about convergence a little bit. So this is an infinite sum. This is an infinite series, and you have to be careful about convergence. It turns out that this converges even only if the real part of the vector z, here z in general is, this is true for, and almost all. I think everybody here is okay with measure theory. So for almost all, but we can be more precise about it. I'll be more precise. For almost all z in c to the d. It's true measure theoretically, but we can be even more precise. It's for all z outside a certain discrete union of hyperplanes. Okay, so this is even only if the real part of z is in the dual cone, where the dual cone is the set of all elements in Euclidean space, whose inner product with everything in X in K So the dual cone is everything that's kind of away from K. So if this is the tangent cone KV, the vertex V, the dual cone is you draw perpendiculars, and so this is the dual cone. So it turns out that there's a very beautiful geometry going on, a duality kind of between cones and dual cones, and it turns out also that this converges even only to a real part of the vector is contained in the dual cone. So far so good? None of this is very difficult, it's easy to do. Okay. So this is the famous Brion theorem. It's a powerful result. It's a powerful result and unexpected. Once you see, so the original proof of Brion, he used toric varieties, vanishing of various cohomology groups. So basically algebraic geometry kind of arguments. But then there are 10, 12 proofs now. I gave another one using Fourier analysis, but there's one using formal power series. To be honest, I think the one in 2024 in this new book, it's good, but it's not perfect. I think it's, to be honest, I think my favorite is still formal power series. You can develop formal power series in a very nice way. It's not just, formal power series has a theory. It's a very nice theory. Anyway, so this is the Brion theorem. There's also, some people call this, including the discrete Brion theorem, there's also a continuous Brion theorem version of this where instead of discrete Fourier transforms, you have the honest Fourier transform, the classical Fourier transforms. And then it's integral is equal to this integral plus that integral, and it's the same thing, except you replace the sums by integrals. There's also that version. So it's very robust. I should mention what I don't know, things I don't know. What I don't know, for example, is in hyperbolic geometry, which is also a very beautiful topic, and I started out in hyperbolic geometry, doing modular forms, number theory, and so on. In hyperbolic geometry, is there an analog of this? I don't know. One would have to consider the geodesics in hyperbolic space. But anyway, so this is the Euclidean space. So far, so good. Still in the back of the dog? Okay. So let me know if you have questions. So this is the discrete Brion theorem. There are singularities, so this is compact, so this is the finite sum. And as we saw in dimension 1 and 2 last time, these are, there are singularities. So there exist singularities here. As we saw, I think it was good to start with an example because the example shows very concretely what's going on. You see we saw the two variable over here on this part of the board last time, yesterday. We saw the two variable rational functions, so you can see clearly where the singularities are and how they cancel. So the cancellation of singularities is kind of a little miracle, and that helps us. So you'll see later today exactly how it helps us. Okay. And so let's continue. Let me write, you're probably curious about the structure of this. Well, you saw the structure of this yesterday for a two-dimensional example. Let me give you the structure in general dimension. So there's a lemma that says that in R to the D, good, right? So, I'll remind you again, well, this integer point transform, it's the same definition no matter what the domain is. You just sum the same exponential, just change the domain. So if I put P for compact polytope, then if I put K for polyhedral infinite cone, then K. If you put pi for half open parallelepiped.
I'm sorry, Professor. Can I mic here?
Yeah.
No, we were capturing the whole room. The microphone was working.
Desliga. Desliga.
Desligado?
Now it's turning.
Now it's working?
Okay.
Thanks. All right. So, yeah, so I guess, yeah, thank you. Obrigado, muito obrigado. So now let's write down the general structure. In general, you have actually, let me write it like this. I'm going to absorb, just to see the structure, where sigma k of z, it's you can absorb the 2 pi I. You see, you can absorb the 2 pi I into the complex vector. There's no harm in that because it's a general z. So 2 pi I times a general complex vector is still another complex vector. So just to start writing things kind of quickly, I'm going to absorb the 2 pi I into the complex vector and just write it as so many people, including Sasha Barvanok, and I like his style a lot, Barvanok will also absorb the 2 pi I. And once the 2 pi I comes from the fact that you have an orthonormal basis of exponentials, and the 2 pi I makes the orthonormality very nice for the basis of exponentials, that's all. Here we don't need it exactly, but when we do need it, we'll change the definition again. But so, all right, so the m's are in K. This is for any, and so now I have to be honest, any simplicial cone, any simplicial cone. What's a simplicial cone? For any simplicial cone K, you have this rational function. So it's a rational function in the variables e to the z1 up to e to the zd. So if you can write this as, you know, e to the z1, and these are integers, so it's e to the z1 times 2 plus e to the z2 times 5 plus e to the z3 times -10, because these are integer vectors. And so it is a rational function, in fact, with integer coordinates, integer coefficients. It's over z, and yeah. So this is obviously a polynomial in these variables. So far, so good. Yes. Okay. So far, and not a big deal, except that it's nice. So what is a simplicial cone? A simplicial cone, a cone K is called simplicial if it has exactly d edges. D edges D linearly independent edges. In general, you can have so if you have D linearly independent edges, for example, in 3 dimensions you have 3 linearly independent edges. They don't have to be integer vectors, but for everything we're doing here, all the theorems that we have yesterday and today and tomorrow, they'll always be integer vectors. In general, you have a simplicial cone like this, but we'll always have integer vectors. And what makes the theory work is precisely the fact that these are integer vectors. That's important to make things work in the theorems. There are extensions, and I've worked on some extensions where you can translate things, and you start with in any case, yeah. So for us, they'll be integer vectors. So maybe I should say, okay, to be precise, that's a simplicial cone, but for us, we'll restrict to integer vectors. So that's a nice lemma. The proof is very easy, but the proof goes via exactly what we did yesterday. Remember, we had a picture over here on this board right here, where we had a half-open parallelogram, and we picked points inside. Each point gave rise to a geometric series in each direction. We multiplied the geometric series, we summed over the points, and so that's exactly what happens to prove this. So these are multiple geometric series. So sometimes when I give courses here at IME-USP, my students, it was kind of a little bit of this, a little bit of analytic number theory sometimes, and I joke that the only thing I really know how to do is sum geometric series, and that's all you really need for all this stuff. Hey, we just proved the theorem the other day. Okay, so that's a simplicial cone. Why simplicial cones? Because if you have a simplicial cone, so if you have a simplicial cone K, let's say this is V, a vertex V, then so if this is W1, W2, W3, then so you have this half-open parallelepiped. You don't include the vertices, by the way. There's another vertex over here. Oh, look. So you don't include. I'm not going to include these. Yeah, this goes off. This is part of the cone. But you do include, so you don't include these vertices. These are open, 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 open. The only vertex you include is this one, due to the definition of half open. So every simplicial cone has this fundamental domain, which tiles the cone by translations with non-negative integer multiples of the w's, non-negative integer multiples. So it's clear, right? And this tiling is what makes the algebra work. So on the one hand, you have geometric tiling, and on the other hand, you have nice algebraic properties, and on the third hand, you have analytic properties. We should really have 3 hands always. We were born with 2, but we should really have 3 or 4 hands. Okay, so far so good? So now let's go, so this is kind of a magical, very powerful theorem. Let's use it. And in order to use it, I'm going to have a little foray, a little diversion into history of Bernoulli polynomials and Barnes polynomials. So I'm just curious, how many know the definition of a Bernoulli polynomial? I don't expect many. So, okay, so that's okay. That's what I figured. So I figured we should go over it. You know how your professors tell you, I'll remind you what it is. What they really mean is, I'll show you what I know you never saw, but I'll pretend that it's reminding you what it is. So let's see what Bernoulli polynomials are. And it's not hard, it'll just take 5 minutes, and then we'll extend it to d dimensions quickly. So historically, well, Bernoulli, there are many Bernoullis, but one of them, I think it's Johann Bernoulli, not Daniel Bernoulli. Bernoulli was curious about how to extend this. You know, everybody knows this formula, but how do you extend it to k powers? Let me go to k minus 1. And Bernoulli was able to do this about 300 years ago. And there are these nice polynomials that extend this very nicely. And these polynomials are called Bernoulli polynomials in his honor. And the formula is exactly this. So you take the n plus first Bernoulli polynomial, which I have not defined yet, and so I have to define this for you in a second. There's a certain polynomial which we'll define. You take the constant term, subtract the constant term, divide by this, and you have a nice formula. These have very magical number theoretic properties, which I'll mention a little bit. So that's Bernoulli. So the definition of the Bernoulli polynomial, which we need to extend to d dimensions, is that you take x e to the tx, you divide by e to the x minus 1, you expand as a power series. And once you expand it as a power series, you just define the coefficients to be the Bernoulli polynomials. And why is it a Taylor series? Why is it's not a Laurent series? If you didn't have this x, it would be a Laurent series because this is entire and this has a simple pole at x equals 1, or x equals 0, sorry. And so it would be, at x equals 0, you would have a Laurent series. It would start with 1 over x. So you put an x there to make it a Taylor series. You put this there just for fun, well, not for fun, to make it, to give polynomials. So the polynomials are exactly these. And this is in hindsight, and I know there's no word in Portuguese for hindsight. I asked many people about this. So there's no analog of the word hindsight exactly. 2020 vision, right? Com perspectiva perfeita atrás. So we say, you know, in hindsight, is there a word?
I think retrospect.
Okay. Close? It's close? Okay. So it's so nice here at USP. There's so many people who are both fluent in Portuguese and English, right? Like these students here, where, yeah, anyway, I learned a lot from my students. All right, so we have this definition of the Bernoulli polynomials, and this is exactly what you use for this. Given this definition, you know, you start with this function of x, you put t as a parameter, it's very easy to show that these are polynomials in t, and in fact, you can start listing them, and they have amazing properties. So for example, one of the properties is d by dt of bk of t is kb, k minus 1 of t. So they have a weird connection between discretizing the indices and differentiating continuously. So it's kind of a mix between continuous and discrete always. It's very, very powerful. What is the connection to zeta function? So just more history. I think everybody knows the Riemann zeta function. If you don't, it's usually defined as this infinite series. I say usually because now there are many, many extensions. And Riemann showed that okay, so I'll be precise. The meromorphic continuation. So you meromorphically continue it, which I think everybody here knows, including the last lecture, if you were the last, so everybody here knows about analytic continuation and meromorphic continuation. Meromorphic just means it's analytic for every S in the complex plane, except for some poles, isolated poles. You know, the singularities break up into 3 classes of singularities, essential, and so on. So here it has a simple pole at S equals 1, but away from the simple pole, it's analytic, and the meromorphic continuation of zeta satisfies, so we'll continue to call it zeta even though it's initially defined by a series. It satisfies the fact if you evaluate at negative integers, you get this precise evaluation at negative integers. So this is a connection between the Bernoulli numbers, which is the constant term of the Bernoulli polynomial, which appears also historically here. What we'd like to do, all this is very simple and already is 300 years old. What we'd like to do is extend this to things like called Shintani zeta functions, which are more current, and Barnes zeta functions. So I'll write down the extension of this in a second to Barnes zeta functions. Barnes, again, was a professor at Cambridge, Trinity College in Cambridge in around 1900. 1901, he published this in 1901 and 1903, and he had a student called Littlewood, which I mentioned, and I didn't know that until I looked into all this, that Littlewood was a student. Anyway, so now we'd like to extend it. So far, so good? There's one also classical extension by Hurwitz I should mention, which is in the same breath almost. Hurwitz defined a zeta function. He said, let's translate the integers by x. So translate, imagine just taking the integers and then translating them to the right by x. So you fix some x positive, you translate all of the integers. If x is positive, this is never 0, as long as, because when n is 0, this is positive, so it's okay. And there's no branch problem of the logarithm because the branch is always defined because it's always positive. So then the theorem of Hurwitz was that the Hurwitz zeta function at negative integers, and you can, the Hurwitz zeta function at s equals minus n, you can sort of guess. Can you guess? Good, yeah, so it's the same formula except the Bernoulli polynomial, where the Riemann zeta gives Bernoulli numbers, the Hurwitz zeta gives Bernoulli polynomials. And so if you extend this to higher dimensions, you want to extend not the Riemann zeta, but really you want to extend the Hurwitz zeta. Make sense? Think of this as a homogeneous linear form in one variable, okay? And think of this as an inhomogeneous linear form in one variable. Okay, all right, so let's see how to extend things. So what are the Barnes polynomials? So far, so good? By the way, just for fun, I asked ChatGPT this morning, what are Barnes polynomials and how do they come up? And he said, oh, they come up in integer point enumeration in polytopes. I said, how do you know? So it sent me to my own paper on the archives. It's kind of funny. And it happens very fast. If you post a paper on the archives, it'll send you to your paper, not after a week, but in fact, after 1 day now. It'll send you to your own article. So now, so Barnes polynomials. So let's see. So instead of looking at this, this was the one-dimensional thing. Now let's start putting parameters in. And I put x to the d because I want an x for each factor. And so each factor has a simple pole at x equals 0. So I want to cancel those poles by putting an x to the d, dimension d. And so this is a very direct and easy extension. And once you expand it in a Taylor series, the expansion, it's a Taylor series in one variable. X is still one variable. So it's going to be something, and x is still one real variable. That something is called the Barnes polynomial by analogy, and it's going to be t and a now. Because now we're introducing a new parameter, a. If you can do this, it turns out, with formal power series. In formal power series, this makes perfect sense, and you can let a, in fact, the vector a, be a complex vector. And we really want a complex vector, as we saw yesterday. So we really want a complex vector A, and t here can be real. So it's fine if t is real. In fact, we can let t be complex, but real is sufficient for us for now. So far, so good. So if you do this, it's very easy to prove just by multiplying both sides by this denominator, expanding. It's very easy to prove that this is a polynomial in t. The degree of the polynomial is k, and it's a rational function in the a's. It's a rational function in the a's. That's also not hard to prove, and it's homogeneous and has a lot of beautiful properties that extend the classical Bernoulli polynomials. And if you do analytic number theory, or if you're curious about the analytic properties, let's write down some of those as well, because it's very beautiful and it extends the Riemann zeta function. So what are the analytic properties? And then I'll show you the combinatorial geometric properties. So far, so good? Still in the back of the dog?
So the Barnes polynomials are polynomials in T, whose coefficients are rational functions?
Yes, exactly. Good. Yeah, so exactly. So this is a polynomial in T in one variable. Yeah, it's exactly as you said, whose coefficients are, in fact, homogeneous. And you can even calculate the degree of the homogeneity, rational functions of these, yeah. So it's not hard to show all this. In fact, there are explicit formulas. And the coefficients of the explicit formulas of the rational function are in terms of Barnes numbers, which I didn't define, but by analogy, you can even guess what a Barnes number. A Bernoulli number is you just evaluate at 0. You look at the constant. Similarly here, you look at the constant of these. Those are called Barnes numbers. So if you let t equal 0, that's the Barnes number. And they extend the Bernoulli numbers, and they should extend the Riemann zeta function to higher dimensional zeta functions. So that's what I want to write down for you to show the precise extension. So let zeta sub d. Now you have a d-dimensional zeta function. And you have, so this extends the Hurwitz zeta function. Yeah, I really want to write it as a linear form. Everybody's okay with this linear form, right? It's m1 a1 plus the usual inner product s. So I could write it as m in z greater than or equal to 0 to the d. That's the same thing. So m is a vector in a positive orthant. In other words, every coordinate of m is greater than or equal to 0. So these are the integer points of the positive orthant. And so this is the Barnes zeta function. So theorem 1901, maybe 1903, by Barnes himself, is that first it has a meromorphic extension in S to all complex S. So S is in C. Okay, I'm not going to say exactly where. The real part of S has to be bigger than D or something. But let me avoid all this. So if you evaluate the meromorphic extension at negative integers, now you can sort of guess by the pattern of these theorems that this should be essentially one of these polynomials. So you get -1 to the n, and I say essentially there's some factorials, n plus d's the dimension, d's the dimension, and then you have b n plus d of t a. So these Barnes polynomials appear as special values. These are called special values of these high dimensional zeta functions. And these are getting very close to Shintani. In the 1960s and 70s, Shintani, who was a brilliant mathematician, discovered that his special values of his, which are very close to this, were a finite linear combination of these. So Shintani realized, in fact, that his zeta functions are a finite linear combination of Barnes. So Barnes are the atomic pieces of Shintani, it turns out. But all these are theorems one has to prove. By the way, for the definition of the Barnes polynomials, we said formal power series is enough, and indeed it is enough. Here, it's not enough. Here, you really need some analytic machinery. But just complex variables in just complex analysis in one variable is already sufficient. Okay, so far so good? To the brain? So yeah, it's very pretty. Now let's go back to combinatorial geometry. Before we go back to combinatorial geometry, any questions? Okay, so the combinatorial geometry is now, we use the same objects. Instead of appearing in classical kind of topics in number theory, they're going to appear in combinatorial geometry now for the first time. So since January, now we know that they also appear in the land of polytopes. And yeah, just again, I said what a simplicial cone is, but I should tell you what a simple polytope is. So a polytope is called simple if exactly the edges, I should say it's in d-dimensional space, the edges meet at each vertex. So a cube is also a simple polytope. In dimension 3, exactly 3 edges meet at every vertex. But you can have more complicated things. You could have even pentagons, as long as at each vertex you have exactly 3 edges. So you have this dodecahedron, for example, which I believe is made of just pentagons. Is it dodecahedron? Yeah. So, and then it's simple also. So you can have very complicated things that are simple. That sounds like a contradiction, but yeah. But it's true, yeah. Okay, so that's a simple polytope, and it's easy to show that this is if and only if in terms of the vertex tangent cones, just to review the definition of vertex tangent cone. At each vertex V, so the vertex tangent cone is the, for shorthand I'll use this notation, which is common notation. So if the W's are the edges of the cone, this is all the positive real span of W1 plus the positive real span of W2, etc. So this is a cone in R to the D, which is generated by the edges. You take the positive real span. Of course, in general, we want the integer points in this, and it's not enough to just put the integers here, because then you skip, as you saw yesterday, we skip some points. But the real cone is this. Okay. All right, so now what's the new stuff? So let me tell you about the new stuff. I was wondering if I should do this here or if I should just be very classical rather than give you the new theorems that I just discovered. But I'm so excited about it, and it's kind of so nice, and it's so elementary at the end of the day that I thought it's appropriate for this venue of Semana Pura, because I think everybody will understand everything. So I think everybody is still on the back of the dog. So let's see. So let me show you the new stuff. And it's always good to tell you what I don't know, not just things we know, but things that we don't know. So first, we'll always pick the edges of our rational cones. So rational means the vertex, that the vertex is a rational point, and these edges will be integer vectors. We'll always pick the edges of the rational cone KV to be integer vectors. So, yeah. So the important thing is that the edges are always integer vectors. And we just need a couple of more definitions. Now you know about the Barnes polynomials. AV, let AV at every vertex. So we fix a vertex V. So you fix a vertex. For us, all the vertices are rational. A rational vertex in general of P everywhere. And you let A sub V be a vector of linear forms. So this is basic linear algebra. And Z The z vector is going to be generic. I guess I didn't say what generic means. Generic is I guess we said in words. Is it okay to just keep generic in words? Generic means, oh, I erased the rational functions in the beginning. Generic means that the generic literally means that the dot product of z with all the with all of the edges is not in 2 pi I z for all edges. So you vary over all the vertices. For each vertex you have d edges, so it's d times the number of vertices. For all of those, d times the number of vertices. For all of those, the same z should not just not be orthogonal. This is not 0, but also not be in 2 pi I times an integer. If it is 2 pi I times an integer, then e to that is equal to 1, and in the denominator you get singularities. So you see now why so this is the very precise generic. So it's even better than measure theoretic because you know exactly where to stay away from. So it's a discrete union of hyperplanes. Not finite, but discrete because of this. So far, so good? So those, you don't need to worry about this. If you don't like it, just think generic. And this is obviously a matrix times the complex C vector, the matrix consisting of whose columns are the edges of the cone. But it's nice to write it in this linear form way. And I think now we have all of the ingredients we need except that I have to tell you what Ehrhart did. Okay, right. So what did Ehrhart do? I mentioned in words, but we didn't write down what he did, right? Right. So Ehrhart, back in the 1960s, was a high school teacher with no mathematical training, and he was completely self-taught and started proving these amazing theorems, amazing results in the 1960s. And so he published it in Krella, one of the oldest journals, I think maybe the oldest journal in all of mathematics. And so so this guy from nowhere starts publishing amazing results in Krella, and then the French government decided, okay, let's give this guy a PhD when he was 65. So he turned 65, he got an honorary PhD. And that was a very nice story of Ehrhart. So in 1962, so Ehrhart, 1962, he proved the following. He said, let P be an integer polytope in R to the D, let T be a positive integer. Then the number of points in the dilate. Is everybody okay with the dilate? So the dilate of an object is the set of all Tx such that x is in the object. So this is the precise definition of a dilate. You just dilate every single point in your object. So the number of points in a dilated object, so if this is a triangle and this is the origin, the second dilate is over here. You just multiply every, so this is P, this is 2P. In a second, we'll also have fractional dilates, all rational dilates. In fact, all real dilates, but he considered just integer dilates. And he proved an amazing result that this is a polynomial in the dilation parameter, very strange. And this polynomial, not only did he prove it's a polynomial, it's easy to see that you get the volume asymptotically. That comes from the Riemann integral definition. But he also proved that you get, so he proved that you get a polynomial. And he also proved that the constant term is always 1. And this is topology. Topologically, this is the Euler characteristic, or technically the reduced Euler characteristic of your polytope. So there's a lot of interesting topology and geometry, two different things, obviously. And so here, this is the number of integer points. And by definition, we'll call it L sub P of T. I think L for lattice maybe it's traditional. Richard Stanley at MIT always calls this E is the Portuguese I sub p for I for integer or L for lattice. Anyway, so this is just but it's really the number of, so you count, and then when you count, you get a polynomial, a kind of a small miracle, or very unexpected. And these coefficients capture the geometry and topology of the polytope. In particular, this is the surface area, essentially, 1/2 the surface area, normalized surface area. And this A1 is the most complex of all. So this A1 is very hard to find in general. The coefficients get more and more complicated as you go down. The intuition is, let's call it C1. The intuition is, so this captures information about the one skeleton. So the graph, in fact, the graph. So it's graph. This becomes graph theory about the graph of the one skeleton of P. And also the kth coefficient captures information about the k skeleton. So in other words, the codimension 2 coefficient will capture information about the codimension 2 faces. So the D-1, the D-2 dimensional faces. That's what we mean by the skeleton, right? The union of all the k-dimensional faces, by definition, is a skeleton. To the bang? So yeah, so Ehrhart did that. He did more, actually. He did a lot more. He also proved the theorem about the rational polytopes. To extend this, let's extend this to rational polytopes. He did that too. He did, in fact, more than that as well. And his ideas were really, really clever. He combined kind of combinatorics with geometry in a very clever way, which we still use today. You cone over, it's called homogenizing the polytope. You homogenize in one dimension higher. He did that too. So theorem, Ehrhart as well. He said fix a rational polytope P, then the number of points is equal to, again, the volume. The leading coefficient, and this is easy asymptotically to show that the leading thing is the volume. But then the next one, instead of being constant, it's a function of t. But the point is that it's a periodic function of t. So it's not so bad. And that was new. These periodic, they're called quasi-polynomials. That was the first instance of a quasi-polynomial. So these are the quasi-coefficients. So Ehrhart proved that where these coefficients are periodic functions of t. But he restricted t to be a positive integer, and in a second we'll let t be any real number. But I wish I could go back in time and show him now our current results. It would be so. So he was the first to do this, and there's a lot of research on the period of this, and very little is known. We don't know much about the periods. Only special family, infinite families, but we don't know in general about the periods of these things. For the coin exchange problems also. So these kind of things, I should mention, they have a lot of combinatorial applications. Let me see what time it is. So I have -2 minutes. I guess I can leave my results to tomorrow if I don't have enough time. How much more should I? 2 minutes? Okay. Yeah. So this is these are called quasi-polynomials. Quasi-polynomials. Now there's a very large literature about quasi-polynomials. And they appear everywhere. They appear in voting. They appear everywhere now, quasi-polynomials. But he was the first kind of to notice that you get quasi-polynomials. So far, so good? He also noticed a lot of other things, Earhart's reciprocity, which we'll mention tomorrow. It's kind of a magical thing between the closure and the interior. This is all for the closure, so by definition, P is always a closed polytope. If you're wondering about the interior, it turns out you can replace T by minus T formally in this polynomial, and magically you get the number of points in the interior. Very strange, but he proved that as well. I'll mention this. And I should mention A0 of 0 equals 1. That's a theorem. Intuitively, this is clear. If you shrink your polytope with the dilation down to 0, you get 1 point, the origin. Intuitively, but you need to make this rigorous. And A0 of t is in general not equal to 1, and it's the most difficult of all of the coefficients. By far the most difficult to obtain. As you can imagine, as you go down, the coefficients become harder, because as you go down, you're talking about the K skeleton. The D minus 1 skeleton, which is the surface area, is kind of the next easiest. But if you go down further, it's finer, 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 and finer. It gets harder. Okay. So now, should I stop here, or should I mention my theorem now? Yeah, okay. Okay, so let me write the new theorem from January. And so I'm going to use this definition of AV, this linear form, these linear forms. So let P be a rational polytope. In R to the D, then L sub P of T, which is by definition the number of points in the, so it's equal to, so -1 to the D over D factorial times the sum over all the vertices V and P, D choose K, and here we go with the Barnes polynomials. So this is the parameter. It's a complex number in the Barnes polynomial, and this is the A, the same A that we had in the definition of the Barnes polynomial. And now there's an interesting new complexity, new element here. Well, all of these, let me write down the difficult part, the part that's, but it's very explicit. So you take this inner product over all the points in a half-open parallelepiped at each vertex. So at each vertex you have a half-open parallelepiped, you subtract T times V, and you work on modulo the half-open parallelepiped. And that's it. These are the explicit. So for the first time, we have explicit formulas for Earhart polynomials. Up until now, we never had explicit formulas. We always had formulas that said, consider the following series, calculate the residue at blah, 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 or take D derivatives and blah. So I was very unhappy with these, including my own paper from a while back. So that's it. So it's not so bad. These are the Barnes polynomials. These are I'm calling polytope Dedekind sums, and we're studying these polytope Dedekind sums as well. And these are discrete moments. So this is kind of spatial statistics. It's the spatial statistics attached to each vertex. You look at moments of this spatial object, the half-open parallelepiped, and you sum over this. Now this is very interesting. So this is the dynamical system. This is a dynamical system. God help me. No, I'm just saying that for João. So it's a dynamical system because, and I'll show you I had ChatGPT yesterday construct a very beautiful, I asked it to construct a simulation of the points moving through the parallelepiped. It's very nice. It took just 5 minutes. If I had to do it by myself, it would take me 5 months, right? But anyway, so it's a dynamical system happening inside this, and this is the flat torus. If you identify the side, it's a flat torus. So you have a torus, compact torus, which is called a flat torus because you consider the model as a flat object in space, flat space, Euclidean space. And so you have this dynamical system as T. Oh, by the way, I should mention then for all, so now we can extend it to all T positive. So for all positive T, not just integers, we have this. And this is a quasi-polynomial. This is a polynomial, and so the quasi part, the periodic part is only here. And so now we've isolated the periodic part to very nice kind of spatial statistic stuff.
I know it's your theorem.
No.
But it's a simple polytope.
Oh, thank you. A rational, simple, thank you. And that's why I had the definition over there, simple polytope. Thank you. Yeah, there's an easy extension to all rational polytopes. It's the same formula for all rational polytopes, but then you have to triangulate every vertex tangent cone. So in general, the vertex tangent cones are not simplicial. Once you triangulate it, then to every simplicial piece of the triangulated one, this applies, and so then you just have to sum over the triangulation as well. So it's a simple extension. Yeah?
What is the Z?
Oh, so the Z, where Z is generic, where Z is a complex vector, generic. Any generic complex vector. Now, you might say, well, wait a second, there's no Z here, you're just counting points, and you'd be right. So the Z's magically cancel. And I was going to show you how the cancellation actually happens in 2 dimensions. It's kind of weird to see this cancellation, but it always magically cancels. So the Z, so it's a very strange theorem. So for the first time, we have these Z's that magically cancel. For the very first time, we have Barnes polynomials, and for the very first time, we have these discrete moments. So all of these are new elements, but they allow you, the Z parameter somehow allows you to calculate, and then it disappears. So it enters, it gives you a way to calculate, and then disappears. Very strange in a sense. The first time this happens in this. Michel Brion discovered something very similar to this for the continuous Brion theorem. He had an application of his continuous, which is a Fourier transform, to volume. So there's something with a much simpler formula for the volume of a simple polytope, where Z enters and disappears. And that was around 1993 or something, 1992. In any case, this is it. So it's not so bad, right? Still on the back of the dog? And here you have a dynamical system. I'll show you pictures of this dynamical system in real time tomorrow, if I can hook up to this. It's very beautiful. And there are a lot of open problems now about these things. So I should mention, if anybody wants to work on this as a PhD student, I'm open to suggestions of PhD students, master's students, and because it's all very new, and there's only so much I can do by myself. I'm doing a lot now, but there's only so much. ChatGPT is doing some too. And I have my own ChatGPTs, Andre and Caio. All right, so yeah, let me stop here. Okay. I like that. Oh, that's cool.
Ok, então, obrigado, Simão.
Ok.
Alguém tem alguma pergunta?